So in this video, we're going to talk about power plant costs. So first, a little bit about the formation of costs, their distribution by time, how do we deal with that, and about the difference of fixed and variable costs. And then we'll have a few slides about cost comparisons between different power plant project options. So first about the distribution of costs by time. So we have basically costs that take place before the plant operation, during the operation, and after the plant operation has finished. So costs that take place before the plant operation, of course, building the power plant itself is the single biggest one of those, but also here are all the costs of building fuel, infrastructure, power grid connections, all kinds of different permits that we need, legal costs, and also the interests that we have to pay for these costs before the plant even starts operation. Then we have the operational costs while the plant is operating, so fuel cost is typically by far the biggest one of these, and then variety of costs like salaries and operating and maintenance cost, insurances, and possible land rent, whatever they might be. And finally we have the post-operation costs, so waste management and decommissioning, and these are of course typically especially high for nuclear power plants, but also have to be dealt with for any kind of power plant that we have finished operating. If we look at the cost structure, so typically the very first costs would take place before the operation even begins. Then once we have decided that, okay, we are going to make this investment, so after the first costs have been paid for, we've got all the permits, and then we start actually building the power plant. That's the big cost that takes place there. Then we have the steady green bar of operating costs, and finally we have the decommissioning cost at the very end. So how do we deal with this is that we calculate so-called levelized cost of energy, where we convert basically everything into costs during the operation. So we are amortizing the investment, and we are considering the total investment as what would be an overnight cost to get all of this paid for overnight, including the interests that we had to pay while all of this was taking place in a couple of years of time, or sometimes much longer than just a couple of years. Okay, then we have also fixed and variable costs. So basically we want to convert fixed costs into specific fixed cost. The fixed part means that this part of the cost is not affected by how much we actually produce energy. Even if we don't actually run the plant at all, we still have to pay all of this fixed cost. And we typically want to give this as specific fixed cost per unit power of the power plant that we built. So capital cost is going to be the single greatest one, almost always practically. And then we have some other fixed costs that typically would be somewhere in the order of a couple of % of the total investment that we have to pay for the plant to get it built. So this couple of % gets paid every year to keep our plant running and operational. Then we have the variable costs, and here as well we want to give this as specific variable costs, and it's now euros per megawatt hour of produced energy. So if we're talking about the power plant, then euros per megawatt hour of electricity, but same principle if it's a heat-only boiler or a CHP plant producing both heat and power, same general principle. And here the fuel cost is going to be the dominant cost, and then we have other variable costs that typically amount to a couple of euros per megawatt hour of electricity. And now if we start to look at the fixed cost, and specifically we start from the capital cost because that was the biggest one. So first of all, we've got total capital investment. We call that TCI with the acronym, and that's the total sum of all the costs to get to the point where we have a power plant ready to start operation. So this includes the plant itself, which is the biggest part typically, but also all the land purchase or rent and permits, planning, engineering, legal costs, and the interests to pay for all of this until we get to the point where we start operating. Then we talk about capital cost. So capital cost is the annual amortization of the TCI. So we've paid a bunch of money and we have to amortize that investment, and we have to pay interest until all of it is amortized. So we levelize this cost for the economic lifetime of our project, and we get a certain annual sum which we call annuity that we have to pay as fixed capital cost every year, and we mark this with CC. And how do we get to the CC from knowing the TCI? We calculate so-called annuity factor. So annuity factor is a function of the interest rate and how long we want to keep amortizing the payment. So basically, if we amortize it very quickly, the annual sum is going to be pretty big, but in the end we end up paying a little bit less interest. If we amortize it over a very long period of time, the annual amortization plus interest is going to be less, but over the total period of time we pay more interest. So we determine the annuity factor based on interest rate and the economic lifetime. We multiply the total capital investment with this annuity factor, and then we get the annual capital cost. This was the biggest part of the fixed costs. We sum to this the other fixed costs, and then we'll get the total annual fixed costs, which we typically mark with capital FC. Now, this was not the term that previously we said that we usually want to give the fixed costs as we want to get the fixed specific cost. Why is that? Because it makes our further calculations further down the line, we'll get to that in a couple of slides, it makes it a little bit more convenient. So basically, once we convert the fixed and the variable costs into specific fixed and variable costs, we can easily calculate pretty much whatever we need to calculate for the power plant. So how do we get to the specific fixed cost? We take the annual fixed cost in euros per year, we divide it with the nominal nameplate power of our power plant, and that's going to be our specific fixed cost. Okay. Now, that was the fixed part. Now let's move to the specific variable cost. So this is the part of the cost that is affected by how much we actually produce energy, electricity and heat. So fuel cost is going to be by far the biggest one typically here. And then we have some other variable costs that typically amount to a couple of euros per megawatt hour of electricity if we have a pure power plant. So first of all, again, to get the terminology straight, we've got the fuel cost. So lowercase c, lowercase to mark that this is specific cost, V for variable, and F for fuel. So F for fuel, and this is set in euros per megawatt hour electricity. So this is the fuel cost per produced electricity that is due to the fuel that we are using. Then we have fuel price, and we shouldn't confuse these two because fuel price is how much we have to pay to get certain amount of fuel delivered to our power plant. And for our calculations, we want to have this in euros per megawatt hour of fuel energy. We typically want to give the fuel energy in lower heating value because this is just typically how it is done in Europe. In United States, it's more often the higher heating value, but here we talk about lower heating value. And we might get the price straight away as euros per megawatt hour. Then we're happy, but sometimes we have to pay for some amount of euros per ton of fuel or kilogram of fuel or cubic meter of fuel, and then we have to convert with the heating value of the fuel and the price per mass or volume or whatever, and then so that we get the fuel price per lower heating value. So for cost calculation, we want to convert the fuel price to fuel cost. The cost per megawatt hour of electricity due to the fuel used. And for this, we have to take into account our efficiency or heat rate. So whatever is the price of our fuel when we purchase it, we must divide by the efficiency to get a bigger number. So for example, if our efficiency is 33%, our fuel cost is going to be 3 times the fuel price. And then from the fuel cost, we get to the specific variable cost. We simply add to the fuel cost the other variable cost. So this other is typically a couple of euros in magnitude, depending a little bit on the type of power plant and where it is operating and so on and so forth. And if we need the total variable cost annually, then we must know how much we are producing electricity annually, and we multiply that amount of energy, electrical energy, or heat energy if we're talking about heat on the plant or whatever it is that we are producing. We multiply that amount of energy with the specific variable cost, and there's our total variable cost. So these are the specific variable cost, specific fixed cost, and then how do we use them to get to the various costs that we might be interested in calculating. So basically, one of the common things that we want to calculate is the cost price of produced electricity. So that means the price we must get from the electricity that we sell so that we reach break even. We are not making any profit, but we're not making loss either. So quite simply, we just take the variable cost as it is, and we add to it the fixed specific cost divided by the amount of time that we are running the plant. The amount of time that we are running a plant, that is not necessarily the total hours that it is producing at least something. So for example, in combined heat and power plants, typically they run a big part of the year at partial load. So we talk about full load hours. So that means that how many hours the plant would have to run at full load to produce in a year the amount that it produces. So in reality, a typical cogeneration plant producing district heat, for example, might run for 6,000 or 7,000 hours per year, and 2/3 of it may be at partial load, so that the full load hours is going to be maybe 5,000 hours or something like that. Then another thing that we might be interested in is the total annual cost. So now we're interested in euros per year, and easy way to remember how it is, and it kind of makes sense when you look at it. So you multiply the specific fixed cost with the power, you multiply the specific variable cost with the amount of electricity produced, and there's your total annual cost in euros per year. And if you forget the equations, it's kind of easy to figure it out how it has to be by just kind of thinking about it logically, and also when you make sure that the dimensions that you get out of it is what you expect to get, then you're probably going to get it right. And finally, what we might be interested in is the annual net cash flow. So then basically you start by calculating the total annual cost. So it's these two later terms here, and they are minus sign because now you want to calculate what is the positive annual net cost. So what is the positive annual net cash flow into your bank account. So negative sign for the costs, and then a positive sign for what income you get from selling the produced electricity. So specific cost of electricity that you are selling times the annual amount of electricity produced. Now, these are fairly straightforward, and then finally on the last slide, a few words about cost comparisons between different project options. So basically evaluating the profitability of different options, comparisons between, or just evaluating your one option, do I do this or do I keep saving the money for some other purpose. Basically we've got 4 basic methods. So first of all of these are based on the same general idea, same general equation. We are considering the time when certain costs take place, so we take into account the time value of money, as it is said, and we can do it in a couple of different ways. And if with given assumptions a project is profitable with one, it's going to be automatically profitable with all of these. But we can use different methods to rank different options, and it might be that one project has a higher net present value, for example, another one is more preferable with some other term. So it's good to be at least somewhat familiar with all of these. So first, starting from the annuity method. So idea here is that we consider the capital costs as we did when we talked about capital costs and how to evaluate that and how to convert the total capital investment into the annual capital cost using the annuity factor. And this allows us to calculate the net cash flow per year. So this means that we are basically discounting the investment through the annuity factor to levelized annual payments until the whole thing is amortized after our economic lifetime. The opposite way of counting the time value of money is with so-called net present value. So that means that we take our total capital investment at year 0, which would be when our plant starts operating, and then we discount all the future profits in the present day. So basically, money that comes after many, many years is less valuable than money that you have right now, because money that you can have right now can grow interest if you invest it smartly, but money that you get same amount of money 10 years down the line, well, that's going to be that amount in 10 years, whereas the same amount of money right now would be in 10 years a lot more. But otherwise the same general idea, and net present value is demonstrated by an example that you will find in the course model page. Then we can also compare by internal rate of return, and we're not going to have any examples of this in the course. It's mathematically a little bit more involved than the other methods, but basically good to understand that it exists and what is the principle. So idea is that we basically calculate with given economic assumptions, what does our interest have to be so that in a given amount of years and a given amount of investment, we amortize the investment. So then you can compare, for example, if you get a certain interest rate, that this would be the internal rate of return for our project, and then you can compare that what if you didn't build a power plant, you decided to invest in the stock market, and how much net growth your investment would have to make per year to make this a better idea than building a power plant. Finally, we have the payback period, where the idea is that we solve for not the interest rate, but for the amount of years that it takes with your given assumptions of profits and total capital investment to pay back the investment. So you can start from the annuity method or an annuity factor, or the net present value method and the net present value factor, and solve for the n in the equation, and then get the number of years, and that's going to be your payback period. So there's also an example of this in the examples in the course Moodle page. So this probably from this explanation, it's not immediately obvious how this works out mathematically, but hopefully the principle is clear now, and then it is best understood when you look at the calculation examples in the Moodle page. How does it all work out in practice? So it's not, there's a lot of terms and different costs and prices, and you have to be always able to keep clear in your head that what price is now per amount of fuel, per amount of electricity produced, or electricity and heat combined, or the specific fixed cost per kilowatt hour, per kilowatt of installed power capacity. But as long as you work methodically and try to keep the concept clear in your mind, and especially I highly recommend to concentrate on those example calculations, make sure you understand how they work. And after that, I believe this should be fairly straightforward stuff.